Los Angeles has a major earthquake fault that never reaches the surface. There is no open crack to follow across a street, no obvious scar cutting through a hillside, and no single line on the ground showing where the danger begins. The Puente Hills Blind Thrust Fault is buried beneath the northern Los Angeles basin, directly below one of the most densely developed metropolitan regions in the United States. A new study published in June 2026 has reconstructed roughly 1.4 million years of movement on its central Santa Fe Springs segment. The result is not evidence that the fault just ruptured. It is more important than that. Researchers found that the deeper fault has been accommodating more movement than the shallow folds above it reveal. And they also found that slip rates changed dramatically through time, ranging from about 0.16 millimeters per year to as much as 2.5 millimeters per year, with a significant acceleration after roughly 200,000 years ago. That changes the interpretation. And the visible surface has been understating what the buried fault was doing below. And the location matters because this is not a remote fault in an empty desert. The Puente Hills system extends for more than 40 kilometers beneath the northern Los Angeles basin, with segments beneath or near downtown Los Angeles, Santa Fe Springs, and the Coyote Hills. The new research does not predict an earthquake. It does not announce a current emergency. It reveals that one of Los Angeles's most consequential hidden structures has a more complicated and more active history than a simple average slip rate can show. That is the real title promise. A fault can move without breaking the surface. It can record its history in folded sediment instead of an exposed trench. And if scientists read only the shallowest part of that fold, they may miss a meaningful portion of the movement taking place deeper underground. The question is not whether Los Angeles has earthquake faults. The question is how much of their behavior remains hidden even after decades of study. For documentaries that follow the evidence beneath familiar landscapes, subscribe and stay with us. This story begins with a fault no one can see, then turns into a lesson about why the most dangerous part of an earthquake source may be the part that leaves the weakest surface clue. The Puente Hills fault is a blind thrust. Thrust fault forms where the crust is being compressed. One block of rock is pushed up and over another along an inclined surface. On many thrust faults, the rupture eventually reaches the ground and creates a visible scarp. A blind thrust stops below the surface, and the fault is still real. The displacement is simply transferred upward into bending, folding, uplift, and subtle deformation of the layers above it. Picture a thick stack of sediment resting over an inclined ramp. As deeper rock moves up that ramp, the overlying layers do not necessarily split open. They can bend into an anticline, a long arch in the strata. New sediment continues accumulating on top, partly burying the evidence of earlier deformation. The landscape may remain smooth. The structural record beneath it does not, and this is why buried faults are so difficult to investigate. A geologist cannot always walk to a fault trace and dig across it. Instead, researchers combine seismic reflection profiles, old petroleum wells, boreholes, dated sediment, earthquake locations, and the geometry of folds. Seismic reflection works by sending controlled vibrations into the ground and recording the echoes that return from buried layers. Different rock boundaries reflect energy in different ways. When the data are processed, the result is a cross-section of the subsurface, almost like an ultrasound image through the crust. For the 2026 study, researchers paired those images with historical well logs and age measurements from sediments. Luminescence dating estimated when mineral grains were last exposed to light. Radiocarbon dating helped constrain younger material. The team then matched layers of similar age across the Santa Fe Springs anticline. Those layers had been lifted and folded by movement below. By measuring how much 7 dated horizons had changed shape, the researchers reconstructed 6 intervals of fault slips spanning approximately 1.4 million years. The crucial innovation was that they did not rely only on the steep front side of the fold. They also examined the gentler back side. That comparison exposed the missing movement. When a deep thrust fault pushes rock upward, some displacement is consumed in building the fold. The front limb may appear to record the main deformation, but the 2026 analysis found that four-limbed growth strata preserved less than 80% of the slip documented in the back limb structure. In plain language, the most obvious shallow deformation did not contain the whole history. The deeper ramp had moved more. This matters because slip rate is one of the central numbers used in earthquake hazard models. It describes the average speed at which displacement accumulates on a fault over a defined period. A higher long-term slip rate can imply that the fault accommodates more regional strain, that earthquakes may occur more frequently, that individual events may involve more displacement, or some combination of those possibilities. But the word average can hide enormous variation. A fault that moves at 1 millimeter per year over a million years does not necessarily creep forward smoothly every day. Most earthquake faults remain locked for long periods. Stress accumulates, then part of the stored deformation is released during an earthquake. The geological rate is reconstructed from many events and long intervals. It is not a live speedometer. That boundary is especially important here. And the new study found rates from about 0.16 to 2.5 millimeters per year across different intervals. Those values do not mean the fault is currently sliding at 2.5 millimeters every year in a way that can be watched in real time, and they show that the fault's role in the regional system changed through geological history. After roughly 200,000 years ago, both the central Santa Fe Springs segment and the western Los Angeles segment appear to have accelerated at about the same time. That synchronous change suggests a kinematic connection. The segments may not behave as isolated machines, and they may share strain across a linked system. This is the first major reveal, and the new paper did not discover the Puente Hills Fault. Scientists identified the system decades ago using petroleum ministry seismic profiles, well data, folds, and relocated earthquakes. What changed in 2026 was the resolution of its long-term movement history. The fault was already known to be important. Now researchers have evidence that its deep slip can be underestimated and that neighboring segments change together. That turns a buried line on a hazard map into a dynamic structure with a history of reorganization. And the Puente Hills system is commonly described as three north-dipping ramp segments: the western Los Angeles segment, the central Santa Fe Springs segment, and the eastern Coyote Hills segment. Together, they extend for more than 40 kilometers beneath the northern Los Angeles basin, and the name Puente Hills can make the fault sound tied to one suburban landscape. Its subsurface reach is much broader, and the western segment lies beneath the urban core of Los Angeles. The central segment passes beneath the industrial and residential landscape around Santa Fe Springs, and the eastern structure continues toward the Coyote Hills and northern Orange County. At the surface, these areas are connected by freeways, rail corridors, warehouses, neighborhoods, schools, hospitals, pipelines, electrical systems, and millions of daily trips. And below them, the crust is being shortened. Southern California is dominated in the public imagination by the San Andreas Fault, a long strike-slip boundary where blocks move mainly sideways, but Los Angeles also sits inside a region of compression created by the geometry of the plate boundary, and that bend makes the surrounding crust harder to slide past cleanly. Part of the motion is converted into squeezing uplift and thrust faulting across the transverse ranges in Los Angeles basin. The result is a network, not one master crack. Strike-slip faults, reverse faults, blind thrusts, and folds divide the strain, and this is why the location matters more than the raw slip rate alone. A fault does not need to be the fastest in California to pose a serious urban hazard. It can matter because it lies close to people, because its rupture directs strong shaking into a basin, because it sits below vulnerable structures, and because its buried geometry makes its past harder to read. The basin beneath Los Angeles adds another layer to the location problem, and seismic waves do not travel through every material in the same way. Hard crystalline rock and thick sedimentary basins can change wave speed, direction, duration, and frequency content. And the Los Angeles basin is filled with deep sediment deposited over millions of years. When earthquake waves enter that structure, some energy can be trapped, redirected, or prolonged. And this does not mean every earthquake beneath the basin will produce the same shaking pattern. The result depends on the source, rupture direction, depth, frequency, and the three-dimensional shape of the basin. One neighborhood may experience stronger motion than another at a similar distance because the waves arrive through different paths and interact with different paths and interact with different soils. For a blind thrust, source geometry matters as much as the map location of an epicenter, and the fault plane dips beneath the city. As rupture moves across that plane, energy may be directed upward and along strike. The hanging wall, the block above the thrust, can experience different motion from the footwall below. That is why a simple circle drawn around an epicenter cannot represent the full hazard. And the fault is a surface in 3 dimensions. The city is a 3-dimensional system above it. When those geometries align badly, proximity becomes more than a matter of miles. It becomes a matter of how the rupture, the basin, and the built environment interact. And the Puente Hills Fault has already demonstrated that hidden does not mean inactive. On October 1st, 1987, a magnitude 5.9 earthquake struck near Whittier Narrows, about 20 kilometers east of downtown Los Angeles. The rupture occurred on a concealed thrust fault at a depth of roughly 15 kilometers. At the time, the source was not recognized as the major buried system later described in detail. The earthquake killed 8 people and caused approximately $358 million in property damage and $1,987. And severe damage was concentrated mainly east of Los Angeles and near the epicenter, especially in districts with vulnerable, unreinforced masonry buildings. The earthquake was moderate. Its consequences were not. Measured horizontal acceleration reached as high as about 0.6 times gravity at some locations within 50 kilometers of the epicenter. Brick walls failed. Chimneys fell. Older commercial districts were damaged. And the event showed that a concealed thrust beneath the metropolitan area could produce intense local shaking without a visible surface rupture. That historical case changes the present interpretation in 2 ways. And first, the buried fault system is not merely a theoretical structure inferred from old sediments. Part of it has generated a damaging modern earthquake. And second, magnitude alone does not determine urban impact. Distance, depth, building type, soil, Basin geometry and the direction in which seismic energy travels can make a moderate event more damaging in one neighborhood than a larger but more distant earthquake. The 1987 rupture did not break the full Puente Hills system. It did not reset the entire fault. It revealed one piece of the hazard. The new 2026 study reaches much farther back beyond the instrumental record and beyond written history. Instead of asking what happened during one earthquake, it asks how the fault's behavior changed across hundreds of thousands of years. That is where the slip rate acceleration becomes important. An earlier work on the western Los Angeles segment found that slip increased from roughly 0.22 millimeters per year in the late Pleistocene to about 1.33 millimeters per year in the Holocene. The new study independently reconstructs the central Santa Fe Springs segment and finds that it also accelerated after approximately 200,000 years ago. The match in timing is difficult to dismiss as a local quirk. It suggests the fault segments are responding to a larger change in how strain is partitioned through the Los Angeles basin. In a useful way to picture, this is not as three separate doors, but as three sections of one buried ramp system. If regional compression shifts, one segment may begin carrying more load. Geometry at the connections can pass deformation along strike. Adjacent faults can also alter how stress enters or leaves the system. And scientists do not yet have a complete movie of that process. They have dated frames, and those frames show that the amount of movement changed. The deeper fault accumulated more slip than the shallow fold alone recorded, and the central and western segments accelerated during the same broad geological period. This is the documentary's largest scientific reframe, and the danger is not that a recent tremor proved a major earthquake is coming. The danger is that long-term hazard models depend on reconstructing movement accurately, and the new evidence shows that the easiest surface record can undercount the motion below, and a model built from an incomplete slip history may assign the wrong share of regional strain to the fault. It may misjudge how movement is divided between segments. It may simplify a system whose rates have changed through time. The latest slip history also raises a deeper modeling question. Which timescale should control the number assigned to a fault? A rate measured across 1.4 million years smooths together many different intervals. A Holocene rate covers a much shorter and more recent window. A geodetic rate measures crustal motion over years or decades, but it may include elastic strain shared among several faults rather than permanent slip on one structure. Each timescale answers a different question, and the long record shows how the system evolved. The shorter geological record may better represent its recent state. Geodesy shows how the region is deforming now, but not exactly which fault will release that deformation next. And the new study does not choose one rate and declare every other estimate obsolete. It provides 6 incremental rates that reveal the variability hidden inside a single average, and this can help modelers test whether the fault should be represented as a steady source or as part of a network whose activity migrates through time. That distinction matters for earthquake simulators. A simulator may distribute regional plate motion among many faults and generate long synthetic catalogs. If the input assumes constant behavior where the geology shows acceleration, the simulated sequence may miss important patterns. If it overreacts to one short interval, it may exaggerate the current role of the fault. The goal is not to make the model dramatic, it is to make the model physically faithful. That does not mean existing Los Angeles hazard maps are useless. It means they must evolve as the fault record improves. Modern seismic hazard assessment combines many kinds of evidence, and fault geometry defines potential rupture surfaces, while slip rates estimate long-term deformation and paleoseismic records constrain past large events. Earthquake catalogs show recent seismicity, geodesy measures present-day crustal motion, and ground motion models estimate how waves may travel through rock and sediment, and no single number controls the result. The new study strengthens one of those inputs. It also exposes an uncertainty that matters beyond Los Angeles. Blind thrusts exist beneath many cities because broad sedimentary basins are attractive places to build. The same sediment that hides the fault can amplify or reshape shaking. The same urban development that obscures surface geology can increase exposure. A buried fault is therefore both a scientific problem and a city planning problem. The built landscape depends on a subsurface structure it cannot see. And in Los Angeles, the consequences are magnified by the arrangement of the metropolitan region. The Puente Hills system lies beneath major transportation and industrial corridors. The northern basin contains dense neighborhoods and older building stock alongside modern engineered structures. Daily movement depends on bridges, freeway interchanges, rail lines, water systems, communications, and power networks that cross the fault's projected area. And the new paper does not calculate what any specific structure will experience. It changes the source model behind that larger question. That distinction protects the science from exaggeration. It would be false to say the study proves downtown Los Angeles is about to be struck, and it would also be false to say a fault's movement history is irrelevant until an earthquake begins. Building codes, retrofit priorities, emergency plans, insurance models, and infrastructure investment All depend on estimates made before the event. And the value of paleoseismology is that it extends the record beyond the short period in which instruments have existed. Los Angeles has only a tiny window of direct earthquake observation compared with the timescale of major faults, and the sediments preserve the longer memory. The Santa Fe Springs anticline is part of that memory. Each period of folding changed the shape of layers deposited by rivers and basin environments. Younger sediment buried older deformation, and later movement folded the stack again. And researchers treated those buried layers as time markers, creating a record that resembles a slow-motion ledger. One horizon records the cumulative effect up to one age, and a younger horizon records a shorter interval. Comparing them reveals how much additional deformation occurred between the two. The method is powerful because it converts structure into history. It is also vulnerable if researchers measure only the most visible part of the fold. That is why the backlimb result matters. Deep fault displacement can be distributed through a broader fold geometry than the front limb alone captures. If less than 80% of deep slip appears in the forelimb record, the missing fraction is not trivial. It can change the estimated rate, and that rate influences hazard. This does not mean every previous number was wrong. Earlier studies used the best available geometry and data, and science advances by discovering where a model simplified the real structure. The 2026 team used 7H correlative horizons and a structural method that accounts for the geometry of the fault ramp. And their 6 incremental rates did not produce one smooth trend. They revealed variation from slow intervals to much faster ones. That variation challenges the idea that a fault has one permanent behavior. Over enough time, faults interact, reorganize, and respond to changes elsewhere in the network. A segment can become more active. Another can slow, the total plate motion continues, but the routes carrying that motion continues. But the routes carrying that motion can change. This is why the phrase has been slipping faster than we knew is more accurate than just moved. The new information is recent, and the movement is not a single recent event. It is a newly resolved history of repeated earthquakes and deformation. And there is also a practical reason to understand how blind thrusts write their history into folds. Surface fault zones can sometimes be protected through setbacks because planners know where rupture may break the ground, and a blind thrust offers no equivalent line to avoid. Its primary hazard is shaking over a broad urban area, not necessarily a narrow surface rupture corridor. That changes the planning problem. Engineers must design for regional ground motion rather than only fault crossing, and transportation agencies must consider multiple points of failure across connected networks. Water and power systems need redundancy because a buried source can affect many corridors at once, and building risk depends strongly on structural type, age, maintenance, and local soil. The science cannot identify which individual building will fail in a future earthquake. It can improve the shaking scenarios used to evaluate classes of structures and infrastructure. This is where the phrase location matters becomes operational rather than rhetorical. A remote fault may mainly threaten the communities closest to it. A fault beneath a major metropolitan basin intersects systems whose disruption can spread through ports, logistics, communications, and supply chains. The physical rupture remains local. The consequences can travel much farther, and the current status is therefore precise. There is no official evidence in this research of a new Puente Hills rupture in 2026. The study does not identify a foreshock, a countdown, or an imminent window, earthquake prediction, specifying the exact time, location, and magnitude of a future event is not currently possible. The paper's contribution is long-term. It shows that hazard beneath Los Angeles may be better represented when deep slip, fold geometry, and time variable rates are included. The next questions follow directly from that result. And how continuous is the acceleration across the 3 Puente Hills segments? How is strain transferred between the Los Angeles, Santa Fe Springs, and Coyote Hills sections? How much deformation is stored on the deep ramp today? How should earthquake simulators represent a fault whose slip rate has changed through time? And researchers will also compare the geological record with present-day geodetic shortening across the basin if the rates do not balance. The missing deformation may be accumulating on neighboring faults, distributed across folds, or hidden in structures that remain poorly resolved. Better earthquake catalogs can reveal small clusters that trace buried fault surfaces. And denser ground motion and deformation measurements can improve models of the basin. New drilling and dating can test whether the same acceleration appears at other locations, but the final answer will not come from one sensor or one study. It will come from fitting many imperfect records into one physical model. And the latest result also changes what counts as a useful next observation. A small earthquake near the mapped fault would be scientifically interesting, but its occurrence alone would not prove that a larger rupture had become more likely. Researchers would need to locate it precisely, determine its focal mechanism, compare it with the three-dimensional fault surface, and examine whether it belongs to an ordinary background sequence. Likewise, a period of quiet would not mean the system had become safe. Locked faults can accumulate strain without producing frequent felt earthquakes, The long sedimentary record exists precisely because the instrumental catalog is too short to describe every important phase of the system, and the meaningful advance is not a dramatic alert. It is a better connection between the slow geological record and the present hazard model. That is, the honest boundary. The new study strengthens concern without converting concern into prediction. It makes the fault more legible without making the future certain. And it explains why location matters. A magnitude 7 earthquake on a distant desert fault and a similar rupture beneath the metropolitan basin are not equivalent problems. The urban fault begins closer to the structures at risk. Its seismic waves travel through a complex bowl of sediment. Its rupture may direct energy unevenly. The infrastructure above it is tightly connected, so failure in one quarter can spread disruption far beyond the strongest shaking. The fault does not need to reach the surface to reach the city, and that is the final physical truth. Imagine downtown Los Angeles on an ordinary morning. Traffic moves through the freeway network, trains cross the basin, and warehouses open along industrial corridors. Water, electricity, fuel, data, and people flow across a landscape that appears fixed. Far below, the Puente Hills Fault rises northward through the crust as a buried ramp. It does not cut the pavement. Instead, its past movement is stored in layers of sediment folded above it in horizons drilled decades ago, in seismic reflections produced by controlled vibrations, and in the pattern of earthquakes too deep to leave a scar. For years, scientists read the front of that fold as the main record. Now the back of the fold has revealed the missing motion. The city above has not changed position in a dramatic instant. Our understanding of what lies beneath it has, and beneath Los Angeles, that difference matters.